Okay, so we're going to do some complex analysis, and the question here is to find the location of the zeros of this function here, z to the 5 minus 3z cubed plus I. Now we've got this complex graph here. We've got a circle of radius 1 and a circle of radius 2. Now we're looking to see if these zeros are located inside the circle of radius 1, circle of radius 2, or outside the circle of radius 2. So how are we going to go about doing that? Well, we can use something called Rouches Theorem. So I'll just write that here. Rouches Theorem. So what we need to do to use Rouches Theorem, we first pick a boundary of one of these circles. So I'm inclined to start with the smallest one first. So this one here has radius 1, or we call it modulus 1. And then we find the dominant term in here when the modulus is 1 of this complex variable z. So if z equals 1, 1 to the 5 is just 1. So z equals 1 here, the modulus of minus 3z cubed is going to be 3. So this term here is dominant for modulus of z equals 1. So I'm just going to write that up here now. So for the modulus of z is less than or equal to 1. So what we do say now, we say g1 of z can equal this dominant term. So we let that equal minus 3z cubed. And then what we do is we take the modulus of f of z minus g1 of z, and we find out what that is minus this term, and that becomes z to the 5 plus I. So we do z to the 5 plus I. We try and work out what that is using the triangle inequality. So using the triangle inequality, we can use a less than or equal sign. Now we can't just say it's equals, because in complex analysis and modulus calculations it wouldn't make any sense. So what we do now is we break this apart by the rules of the triangle inequality. So now we take the z to the 5, take the modulus of that, then the I. So then plus the modulus of I. Okay, for z is 1. 1 to the 5 plus 1, that equals 2. Now g1 of z minus 3z cubed, so let's work out what that is. So the modulus of minus 3z cubed, so I'm breaking that down by the triangle inequality. We have the modulus of minus 3 times modulus of z cubed. So 3 times z cubed, that's just going to give us 3. So as this 2 here is less than 3, i.e. this value here, what we can say is that the number of zeros inside here is equivalent to this zeros of this function here. So as it's minus 3z cubed, this will have 3 zeros. So therefore there's 3 zeros inside here. So 3 zeros inside here. So that takes care of the first circle there. And as the function here, the polynomial is analytic all the way through the values of z equals 1, then this will hold for Rouché's theorem. So the next thing we look at, the modulus of z is less than or equal to 2. So now we're going to find the zeros inside this line. Now it's going to be all the way to the origin, but then we know what the values are inside here. So we need to work out how many zeros are inside here. So if the modulus of z is 2, the dominant term here is going to be the z to the 5. So now we let g2 to the z equal z to the 5. And then z to the 5, we'll just write that as the modulus of z to the 5, which is less than or equal to z to the 5. And when modulus of z is 2, 2 to the power of 5 is 2, 4, 8, 16, 32. So that equals 32. Okay, so now we'll take care of this part of the triangle inequality. So f of z minus g2 of z, take the modulus of that. That then becomes this function minus this function, which is minus 3z cubed plus I. Okay, so using the triangle inequality, less than or equal to minus 3 z cubed plus modulus of I. Okay, modulus of minus 3, that just becomes 3. Z cubed, when z is 2, that becomes 8, so that becomes 24, plus 1, that's 25. So, and as 25 is less than 32, we say the zeros inside this circle are equivalent to the number of zeros of this term, which is 5. So what we can say is in here, there is 5 zeros. Okay, just checking for the boundaries 1 and 2, and we can also check for 0. We can see 0 is not a solution for this, so if you say z to the 5 minus 3z cubed plus I equals 0, we can see that z is 2, it's not a solution for that, I'll let you guys work that out. Z is 1, it's not a solution, and also for z is 0, it's not a solution. So there's no solutions on the boundaries. So therefore they're going to be within the parameters of these circles. And then we can say z to the 5 minus 3z cubed plus I. This is going to have 5 zeros located in it somewhere. And we've also calculated there's 5 zeros inside this perimeter with radius 2. So therefore there's 0 zeros outside of this perimeter here. So what we can say is by fundamental theorem of arithmetic, 5 zeros is in here and 3 zeros is near, so therefore there is going to be 2 zeros in this part and 3 zeros in this part. So we say by Rouchez theorem there are 2 zeros inside the set where z, let's say modulus of z, let's just rewrite that a little bit different, fit room, is inside 1 modulus of z 2. So there's 2 zeros inside this point and 3 zeros inside 0 modulus of z and less than 1. So that's going to be the location of all the zeros of this function here. Okay.